and energy extraction on horizon scale. And yeah, all of them will be talking about M87 and not Sagittarius star. So I'm sorry for those Galactic Center fans in the audience. So
You only get half a sandwich.
exactly. Okay. Yeah, so here's M87, which I think is a beautiful source, very close by source, and a lovely example of an extragalactic jet that we can observe in really fine detail. It's the first extragalactic jet discovered over 100 years ago at this point, and over the last 100 years, people with successively finer resolution and using VLBI, interferometry and then VLBI have zoomed into the core of this jet. Until a few years ago, this was the highest resolution image we had at 3.5 millimeters. And then, of course, while I was here in this building, I was able to work on the first image on horizon scales with the AHT, which shows us the environment right around the supermassive black hole that we think is launching this jet. And of course, I don't need to remind this audience what the AHT is. It's a collection of radio telescopes all around the world operating at 1.3 millimeters. And just by happy coincidence, this turns out to be just enough resolving power if we just divide 1.3 millimeters over the diameter of the Earth to just barely pick out the event horizon scale structure in M87. And of course, many people in this room are working on expanding this array and making it more capable, which I'll talk about a little bit later in the talk. So what do I think about? I think about a variety of questions related to M87, but one that I'm going to spend the most of this talk talking about is this jet launched by extractive black hole spin energy? This is sort of a commonly understood picture for what launches extragalactic jets. It's this Blanford zodiac mechanism that takes out spin energy of the black hole through magnetic fields and powers this large jet, taking energy to very large scales. But what I'm really interested in, at least lately, has been, can we sort of observe this process up close or constrain it on the event horizon scales that the EHT is looking at? Other questions I think about, which I won't talk about through much of the talk, but if you can ask me questions or talk to me later, are things about how we can perform tests of gravity with the EHT and about how plasma processes energize electrons and light up the flow and determine exactly what we see in these near horizon scale images. Okay, so in this talk, I'm going to talk about 3 different projects. First, I'm going to summarize sort of the canonical EHT results from polarization of the black hole. Many people in this room are probably very familiar with these at this point, so but I think it'd be good to get background, especially on our latest results on circular polarization that just came out last fall. Then I'm going to jump to a paper that I recently did with some colleagues at Princeton, looking at how we can connect these polarized images to energy flow and jet launching on horizon scales. And then lastly, if I have time, I'll talk a little bit about how we can maybe improve these simulations that we use as sort of the cornerstone of some of our analyses of these systems. Okay. So before I begin, I have to, of course, emphasize that a lot of this work, especially in the first part of the talk, was done not just by me, but by the whole Event Horizon Telescope group. The Event Horizon Telescope is not just a telescope, it's also a group of people, now at this point spanning over 300 members and over 20 countries. Here's just a picture of some of us at the latest collaboration meeting. Okay, so in the first part of the talk, I'll talk about what we learned from the first polarized images of the black hole. And this is summarizing these 3 papers, first 2 from 2021, looking at the linear polarization of M87, and then the second from just last year in 2023, looking at the circular polarization. And just like, and to emphasize the fact that this was done in the context of a large collaboration, I also want to emphasize that these particular results were done by a relatively small subset of that group, many of whom are in this audience right now. But this is just the sort of core team behind EHT papers 7, 8, and 9, looking at the polarization of M87. Okay, so why are we interested in polarization? Well, it's basically because we're interested in magnetic fields. And synchrotron radiation is emitted with polarization perpendicular, its polarization direction, linear polarization direction perpendicular to magnetic field lines. So the ideal case where we just have synchrotron emission and we don't have any intermediate propagation effects, we can just use the polarization image to directly learn about the magnetic field structure in the emission region. And if we have sort of a prediction of what the magnetic field structure in the emission region might be from, say, a Blanford zodiac model of a jet, we can then just immediately say, is this prediction consistent with our data? Of course, there's a lot more complications to this that we had to deal with in the EHT papers, particularly to polarization transport. So the fact that we're not just seeing a clean image of the emitted polarization, but it's traveling through this plasma, through this curved space-time, both of which are doing things to alter the polarization image that we see. But the good news is that this polarization transport effects, though they're complicated, are also sensitive to things that we want to learn about, like the magnetic field, plasma parameters, and spacetime. So the canonical tools that we in the collaboration have sort of used to interpret these results, these images, are this combination of GR-MHD, general relativistic linear hydrodynamic simulations, and GR radio transfer codes. So I'm sure everyone's very familiar with this, but we basically solve the coupled equations of plasma dynamics and magnetic field in the curved background. The image of which, movie of which is on the left, where you have the density falling into the black hole and then being expelled in a jet here on the right, and this slice through the vertical plane of a black hole simulation. And then we take those simulations with all their complicated dynamics, which self-consistently couple the disk and the jet, and we observe them, quote unquote, by solving the equations of synchrotron radio transfer through the curved geodesics in the space-time. And so you get these beautiful images like this, which show things like the direct emission around the black hole, the highly lensed photon ring, and all this interesting polarization structure and dynamics, which you want to interpret. And of course, the sort of key dichotomy in these simulations that are one of the key things that we wanted to test back when we were first looking at these images, while I was here at the BHI, and then later as we were working on the first polarized images, is what is the magnetic field structure close to the horizon? And we sort of had two distinct accretion states in this sort of set of simulations that we had been looking at for a long time. These two accretion states depend on the amount of magnetic flux on the horizon. They're really quite distinct in their dynamics and their structure. And so on the left, you have this sort of classic turbulent magnetic field case where the magnetic fields are weak, they're sheared out, they still can pile onto the black hole and form an outflow or a jet, but in the accretion disk itself, they're weak and turbulent and form all these little bubbles and things. This is called the sane or standard and normal picture of accretion. On the right here, we have this magnetically arrested case where instead the fields are coherent and have a lot more strength and order in the disk on even up to pretty large scales. And so you can see in this snapshot of this simulation here that the fields, even in the disk, are ordered. They build up magnetic flux on the black hole. And I should say that strong fields here for M87 means like 10 to 100 Gauss. So strong relative to the size of the black hole. And of course, understanding which of these is more likely to be operative around M87 is really important for understanding how jets are launched. Of course, jets can be launched in both of these cases. You can see an outflowing funnel in both of them. If you just look at the simulation snapshot. But jets are more easily launched by the hydrodynamic mechanisms if you have more magnetic flux. And so if you can tell what the magnetic flux on the black hole is in M87, you can learn things about, like, for example, how high does the black hole spin have to be in order to power a similarly large jet, because the jet power in BZ goes as magnetic flux squared times the spin squared.
Is a weak magnetic field automatically turbulent and a strong one automatically coherent?
I guess not necessarily, because, for example, in the same case, right, you still have ordered fields in the polar region, but they're weaker typically. But yeah, I guess in the way that the simulations usually have their boundary conditions, at least, these things tend to be correlated.
So is turbulent and strong and coherent and weak, are those ruled out?
I think there's still a lot of questions about, whether we're fully exploring the space of boundary conditions for these simulations. And so it's possible that there are other states that have not yet been.
I think one can say, at least in the disk region.
Yeah.
If your field is weak, then the gas is the boss. And it can, wrap up the field like it's
Right,
doing
so
with the
that turbulence is really the turbulence of the gas and
It is the
that's
turbulence
it's
of-
dragged around, that drags around the magnetic field.
Yes, that's
Yeah.
the one way to look
Yeah.
at it.
Yeah.
And the guy on the right, the field is strong. It's so strong that it's the boss. And even if the gas wants to become turbulent, it's not allowed to.
I see.
Okay.
So this is in some approximation, the magnetic Navier-Stokes, roughly relativistic magnetic Navier-Stokes, is that what that is? On the left, yeah,
MHD turbulence, yeah.
yeah,
Yeah, but in a rotating frame, so there are extra complications.
correct.
Yeah,
That's a
Yes.
related question. So magnetorotational instability makes everything shed angular momentum and creep. Are there different ways of looking at that process between these two? I mean, are they both operating in both SAT and main?
I think this is a topic of ongoing investigation that people have different opinions about, but I will not get into that. But yeah, there's, I think, a variety of processes that happen in both. I think, yeah, certainly in the same case, it's the MRI that is causing things to fall in. I think in the MAD case, flux eruptions might also play a role. Mesh nodes all about this.
Yeah, like you say, it's debated, and I think there is no MRI in the MAD case. MRI has been killed by the strong field. And instead, yeah, it's these flux eruptions and other things that are carrying the angular momentum away.
So is there simple, so these two pictures look so very different, right? But from the image, you can't really tell them apart so easily, right?
That's
That's
what
what
we'll
you're
be
about to get
talking about. Yes, so exactly as Andy said, when we first looked at these images back in total intensity, only in total intensity back in 2019, we had the first set of images from the EHT, and we wanted to compare them to simulated images. So we run through our whole pipeline. And the interesting or potentially disappointing fact that we observed was that all these images looked relatively the same once you sort of tweak the free parameters like the total intensity and the overall size. And so here, for example, in this first EHT paper 5, you can see two sane models and a MAD model in total intensity, and they all look more or less the same. I couldn't pick these out by eye. Maybe people who have stared at them more could. If we add an additional constraint on jet power to EHT sort of constraints that we apply in those papers, we could reject spin zero models. This, I think, is telling us that in the simulations, the jet really is launched by BZ. Spin zero models can't launch jets that are powerful enough to fit our understanding of M87. But overall, our constraints on the structure of the accretion flow and the whether it was we're in the sane or MAD picture were very weak. And so the question was immediately, can we do better when we have polarized data, which tells us more about the magnetic fields? Before I get to the polarized interpretation, just recap exactly what the polarized image looks like. So on the left is our first image of M87 total intensity. On the right is our first image of M87 in polarization from EHT paper 7 in 2021. And here we have the total intensity image in grayscale underneath the ticks, which encodes the direction of the linear polarization vector and its fractional polarization in the color. And just by looking at this image, you can see immediately that the polarization is concentrated in the southwest, that its structure is sort of predominantly helical. This helix has a particular sign. And the overall level of polarization is somewhat weak, sort of 15%, which is much lower than you would expect just from sort of pure synchrotron emission, which tends to be closer to 70%. Okay. So a lot of our work in the first interpretation papers interpreting this image was sort of trying to understand the effect of propagation effects, particularly GR and Faraday effects, on sort of this ruining the simple relation between the polarization that we observe and the underlying magnetic field direction. So we spent a lot of time trying to parse out these individual effects, which I won't get into too much detail on, but I will talk about Faraday very briefly. So Faraday rotation is the effect where as you send a polarized light ray through plasma, its direction of polarization rotates depending on how much magnetic field and plasma density you have along the line of sight. And so you can see this in this animation. What this does to EHT images of M87 on scale, sort of infinite resolution scales, is it scrambles up all of our polarization vectors. So here on the right, you can see an image where we've just turned, from our simulation library, we've just turned the Faraday rotation effect off, and you can see all these polarization ticks are like sort of neatly aligned along these magnetic field lines, these spiral arms which have magnetic field threading them. But if we turn Faraday rotation on and include all the propagation effects that we know to be operating in the plasma around M87, we can see that these polarization ticks are still scrambled. The overall fractional polarization or degree of polarization is still high in both cases at the scale, at this sort of infinite resolution scale, but the ticks are scrambled in the case where we include the propagation, the Faraday rotation.
Can you use dispersion measure to make the reverse transformation since you now know the electron density?
So we can estimate the Faraday rotation measure and derotate it or attempt to do that. But we think a lot of this rotation is happening internally to the emission region. So you can see that these ticks are being rotated by different amounts. It's not sort of a coherent thing in the simulation. There's no single screen that's rotating everything by the same. But yeah, so once you blur this to the resolution of the EHT, however, you get, which again, we can only sort of observe with 20 microarcsecond resolution, you get this effect where in the case without rotation, you still see very high fractional polarization because, you know, even though the polarization structure is changing a little bit under the scale of the EHT's beam, this blurring kernel that degrades the resolution, it's not changing so much that you lose this strong polarization by coherently averaging all those vectors together.
So it'd be more depolarization in a turbulent, sane scenario than in the.
Yes, that's right. But I think still not enough to account for this overall degradation in most cases. There's, yes, Angelo is an expert on this, and there's also a lot of discussion in the papers. But yes, with rotation, you get this overall depolarization from this scrambling effect from the fact that the plasma is passing through different sort of pockets of local magnetic field.
As it rotates the pattern.
Yeah, so this is a question I think is going to be very important in the future. I think sort of understanding exactly how, I think the way to think about it is that there's sort of a turbulent component of the Faraday rotation measure and a sort of an average component. The average component, I think, is sort of rotating the whole pattern, and the turbulent component is sort of rotating things in the individual pixels, which then get blurred out. But exactly how to do that decomposition for Faraday rotation that's internal to the emission region is something I think I would at least like to have a better understanding.
Even if there are,
In this particular example that you've shown, the turbulent scrambling has definitely decreased the degree of polarization. But the mean rotation is practically zero.
Yes, that's correct.
Okay.
Yeah, so we're operating in M87 at a case where, at least in these simulations, where the overall rotation measure was not very high. So you can just measure it, and these simulations sort of agree with to that order of magnitude, and it's like a few degrees at 230 gigahertz, right? Maybe 10.
Only a few degrees,
Yeah.
but there's a lot of scrambling and
Yeah, you could imagine a situation where the Faraday rotation was an order of magnitude higher. There was also a lot of scrambling, but then also an overall shift.
Yeah.
That's much larger. So that's something I think we have to.
even if the rotation is large by itself, observing at neighboring frequencies can
Yes.
give you a small differential rotation.
Absolutely.
There's no gravitational polarization rotation in this.
Oh yeah, both of these have the gravitational parallel transport effect. So both of these include all the propagation effects through the curved space-time, but we just artificially turned off the plasma rotation on the one.
I see.
Okay, so incorporating this Faraday effect is very important. So we include itself consistently in producing simulated images from our simulations. We look at a large library of simulations. Here's a sort of a pane of images, both at their native resolution and the EHT resolution. And we try to look at all these images and their input and score them against the images that we produced from the EHT. And a lot of the different images that we have here in these panels correspond to different electron temperature models. This isn't something I'm going to talk about much, but it's a very important systematic that we don't really know much about how the electrons are heated in the flow. So ask me questions about that if you know. Okay, so I won't get into the details of how we do this, but basically the point of this slide is here on the right, where you can see that where it's in total intensity, all of our simulations look very similar. In polarization, they look very different. And so you can see the GRMHD images, which all might do well on the total intensity cuts, in polarization can be strongly or weakly polarized. They can have patterns that are helical or radial. Look at eye, they look very different. And so we know immediately that we can learn a lot more with polarization than we can with full intensity. And so what we do is we sort of score all of these simulation snapshots against a variety of metrics, which we also compare to the real image. I'll get into those metrics in detail, but the important one to remember for the rest of the talk is this beta 2 metric, which is basically the second Fourier mode of the polarization pattern taken around the ring, introduced by Daniel Colombo of here, who in 2020, a seminal paper of 2020. This sort of encodes this polarization pattern around the ring, and it turned out to be the most constraining metric. And you can just sort of see that immediately by looking at a histogram of all of the phase of beta 2. So this is the quantity we're talking most about. This is the argument of this complex number for the phase. And just by looking at this histogram of all of our simulations compared to the range that we established for M87 here in blue, you can tell immediately that this is going to be a very constraining parameter because many simulations produce things that are not in this small band. You can also tell immediately that most simulations produce things which are less than 0 in this beta 2 phase, which I will come back to. Yeah, and to understand this beta 2, it might help to have this sort of picture in your head where it sort of corresponds to EMB modes in cosmology, right? Where it's telling you something about whether the polarization structure is radial or azimuthal. If it's real, positive, or negative, it does correspond to those two modes. But if beta 2 is imaginary, it's sort of in one of these two helical states. Okay, so we have all these metrics. We compare them to the simulated images, to the real images, and we, at the end of the day, do this with a variety of approaches, but all of them strongly favor these magnetically arrested or mad accretion disks. And so the simplest way to see this is just with looking at the total number of passing images, the total number of images which satisfy all of our constraints simultaneously. And you can see that except for just a very few sane images, almost all of them are MADs. And we can do this scoring in a variety of ways, and they all give us roughly the same answer, which is that these MAD models are vastly favored over the sane models. So from this polarization scoring, we've learned that the magnetic field in M87 is much more likely to be in this highly ordered, strong configuration where there's a lot of flux in the black hole and it can more efficiently launch a jet. From this, we're also able to constrain M87's accretion rate by 2 orders of magnitude. So now there's only a 1 order of magnitude uncertainty in it. And yeah, learn that we have these strong fields which are much more likely to launch jets at even low values of spin. Okay. So the last couple slides in this section, I want to do briefly highlight the latest update to these results, which was from this fall, which is our analysis of circular polarization. I won't get into too much detail, but basically everything I said previously was in linear polarization. So you might ask, what can we learn from circular polarization? And the good news is that the EHT was able to detect unambiguously that there is circular polarization on horizon scales. We did this with this complicated closure phase difference metric. Basically, we see in these most robust quantities that we observe with the EHT, which are these closure phases, we see a systematic difference between the closure phase we observe in the right-right polarization and the left-left polarization. That's sort of a telltale sign there must be circular polarization that we're observing on these scales. This is immune to a variety of corrupting effects. So the good news is we know that this circular polarization is there. The bad news is that we were unable to produce consistent images of it. And this is just because circular polarization in M87 is 10 times weaker than the linear polarization. It's already 10 times weaker than the total intensity. So we're operating at really low signal to noise. And basically our imaging methods with the low signal to noise and the very sparse data that we have aren't able to get a consistent reconstruction. And so in particular, we did what we always do with the EHT, which is throw a bunch of methods at the problem, only focus on the consistent results that between methods to really try and emphasize the most conservative conclusions that we could. And we found that different methods for reconstructing the data don't show consistent circular polarization images between days or between frequency bands. You can see that here where the total intensity images in the contours, that all looks consistent. It's great. But the circular polarization images in the color, the red and blue, you can see that that just isn't consistent between methods or days. We were able to place an upper limit on this quantity of 3.7%. And future observations should be a lot more sensitive. So we should be able to hone in on this image, hopefully, in future years' data. The good news for theory is that the simulations already naturally produce this very low circular polarization. So you can see that, I think here, where basically only a long tail of these simulations is produce circular polarization that's higher than our upper limit.
Andrew, could you go to the previous slide?
Yes.
I was just looking at the bottom row. Right, this is April 16th, whatever low band.
Yes.
There is one method, Themis, which produces entirely blue. And then diff map entirely in red.
Yep.
So I thought that at least, the data should tell you are you mostly red or blue, right?
Yes.
How can this happen?
I think the diff map one here is an outlier. Most of them do produce overall blue, because I think, yeah, the overall EMAT was more negative.
Okay, so I just should.
I would ignore this.
Okay, thank you.
Just one question.
Yeah.
So when you do these images, you're solving simultaneously for calibration
Yes.
in some sense.
Well, all the methods are doing very different approaches to this, but yes.
So the calibration can change blue to red.
Well, that's what I'm getting at.
Yeah.
Yeah.
From the instrumental perspective, are they finding convergence on what the instrument is doing, but they're just recovering different images?
So the main systematic is this gain ratios of right over left, and no, I don't think that people have convergence in those quantities. But yes, that could potentially change the science. So it's possible that in this particular image, they just had a crazy gain ratio, which maybe we should have excluded, but the overall picture I don't think is changed by that one image being a little bit.
The reason I'm asking is you could think of calibration techniques at the telescopes that would try to address this. So being able to map this back to the instrument is really.
Like I said, I'm very hopeful than in future years, just with the fact that we have more telescopes, we have more baselines between them, we get more signal to noise, we'll be able to harness this. Okay. Reading behind, but the main takeaway for the positive view, and this is a nice figure that Angelo made, is that the simulations that pass the linear polarization constraints all have diverse circular polarization morphologies. And so you can see just a collection of these simulations, all of which pass in linear polarization and circular polarization look quite different. And there's a lot of work still to do on understanding the implications of circular polarization images and what we might learn with better results from the EHT on circular polarization. I think Angelo is the expert on this, but definitely there's more work to do. Okay, so that's just a summary of where we are for the EHT results. And the next section, I'm going to talk about how we can sort of interpret some of these results a little more physically with toy models, essentially. Can we connect the polarized image of M87 on horizon scales to these sort of fundamental questions about energy flow and jet launching, which we're really interested in understanding. And this is a paper that came out last year. Yes, as motivation, of course, M87 launches this beautiful jet. We spent a lot of time thinking about the structure on very small scales, but at the same time as the EHT observed in 2017, we had this massive multi-wavelength campaign that we did, and we observed it on all these different scales across this huge span of wavelengths, and most of the images are dominated by the jet. And this jet is thought to be powered by black hole spin energy, but we really want to know, can we answer that definitively or not on these scales close to the horizon that we're looking at with the EHT. I think we have a lot of indirect evidence that the jet is powered by BZ. One of the, for me, best pieces of indirect evidence is that all the simulations clearly have jets that are powered by Z, and the simulations can do a pretty good job of producing jets that look like M87s. So the fact that the jets from MAD simulations or even SANE simulations are powered by spin has been known for a while. And simulations like these, which I did while I was here at the BHI, naturally produce jets which look a lot like M87s. They have power in the right range. They have observations of opening and going Porsche, which look like the real data. But I think we still want to know if there's a physical quantity that we can connect to energy flow on these horizon scales.
Is there an alternative to the jet being powered by the spin?
Yes, I should have said that. So the alternative picture for the jet being powered by the spin is that it's powered by sort of the accretion disk. So you have magnetic fields. This is the Blanford-Payne mechanism as opposed to BZ. So you have fields that don't thread the black hole and extract energy from it, but extract energy from the angular momentum of the accretion disk. But that is not seen to be a significant component of the energy.
There's
flow.
enough. There doesn't seem to be quite as much energy in the angular momentum of the accretion disk, right? But somehow that.
Yeah, I
it's a
guess
viable
like when you're pretty close to the event, if you have an accretion disk whose inner edge truncates pretty close to the horizon, there's still a lot of energy there that you could potentially extract if that's where the fields are truly anchored. I think in the real system, right, you have energy outflowing from the horizon, but then also from various scales in the accretion disk, and so it's sort of a mix between the two. But in the simulations, it's definitely the BZ component that dominates. Except potentially maybe in very low spin simulations. Okay. So yes, just to reground ourselves in the image, the question then becomes if we know that this beta-2 metric is sort of the most constraining in simulations. If we just look at what gave us the most power for connecting simulations to data, there was this beta-2. And so it's sort of a natural candidate to understand, can we use this beta-2 we interpret this beta-2 physically? We interpret this sort of direction of the polarization spiral physically and connect it to energy flow.
I have a question.
Yes.
So I read some beta-2 analysis depends on the choice of origin on the image.
Yeah.
How do we decide the origin?
Yeah, so this is a very good question. When it comes to the actual images, what we tend to do is we tend to fit a ring to them and then use the center of the ring as the center of the beta-2. When it comes to the simulated images, we tend to just take the center coordinate of the image as our beta-2 center. We've done some tests, especially in paper 7 and 8, on like how important that offset can be. And it's not very important, but it might become more important as the images get better. So,
Okay,
it's a very
so you decide from the total intensity links.
yeah, exactly. So we sort of find what the best ring in this image is, and then we center the beta-2 there.
Okay. From the
Total intensity image, yeah.
gray scales.
Yeah, the polarization is sort of so asymmetric that if you just look at polarization itself, it wouldn't form a nice ring. So in order to interpret this beta 2 physically, I'm going to ignore all of the important propagation effects and Faraday rotation and GR parallel transport that I said were very important, and they remain important, but let's just step back and look at a cartoon picture. So this is sort of the simplest thing you could possibly think about, which is magnetic field in flat space looked on straight down, where the coordinate axis is into the screen, as we think the black hole spin is into the screen for M87 from the overall asymmetry of the image. And so here I've just sort of drawn these four fiducial beta 2 modes, this radial beta 2 equals angle of beta 2 equals 0, this sort of toroidal angle of beta 2 equals plus or minus pi, and the two opposite-handed helixes. And I've drawn underneath them the magnetic field lines, which are just rotated by 90 degrees. So this is sort of the simplest interpretation you could have of beta 2 if you ignored all the very important propagation effects that we have to consider in our full analysis. And I think the key thing to get from here is that our spiral of polarization ticks in the M87 image is this right-handed spiral here on the right, corresponding to an argument of beta 2 or an angle of beta 2 that is negative, so between 0 and minus pi. And if you just flip that spiral by 90 degrees to get the underlying magnetic field structure, you have a left-handed spiral indicated by here, which corresponds to a ratio between B phi over BR, or tangent of the pitch angle, being less than 0.
Question.
Yeah.
So how far away are we, like here, where's the horizon and the ergosphere?
Yeah, so this is, again, a very cartoon picture. We don't even have a notion of where the black hole is. But if you sort of say this was the M87 ring that we're observing,
Yeah.
this is sort of at emission at a radius of 5 gravitational radii roughly. So 2.5 short field radii.
So it's very close, but very far outside the ergosphere.
Yeah, it probably has some components from inside there. So yeah, I think largely around that too. Yeah, I think mostly outside. But that might change also if we have higher frequency. Okay. So yeah, this is a very cartoon picture. The important part is that we think if we just take this cartoon picture literally, we have this particular sign of the ratio B phi over BR. And so I think the thing which we realized, which hadn't been pointed out in this paper, that hadn't been pointed out in the past EHT papers, is that it's exactly this relative sign of B phi over BR, which is important for determining the sign of the energy flow in sort of simple models of the BZ mechanism. And in particular, if you have sort of axisymmetric, stationary electromagnetic fields in either GRMHD or even in force-free dynamics, the radial pointing flux depends on exactly these two components of the field. So it's proportional to the negative sign of BR times B phi times omega f, which is the angular speed of the field lines. And so, again, we think in M87, the black hole spin direction is into the screen. That's one of our earliest conclusions from 2019. And so if you assume magnetic field lines are co-rotating with that, and so have a positive angular speed, depending on this setup of our coordinate axes, this sort of exact ratio B phi over BR less than 0 tells you immediately in this cartoon picture that you have energy outflow on these scales from these magnetic fields under all these very large assumptions, which we've made about this equation being valid formally only in the case where you have axisymmetric fields, under the case where we have no Faraday rotation or GR propagation effects or anything. But still, I think it's a very intriguing connection, which hadn't been drawn out explicitly before. In contrast, if we had observed the opposite sign of the helix, and we had seen a beta 2 that was greater than 0, that would have told us in the simple model that we have energy inflow, or more likely that either our inference about the field line angular speed or something about the Faraday rotation or any of these complicated effects were wrong. But I think the fact that everything is consistent in the simple picture is really intriguing.
Andrew?
Yes.
Does this depend on an interpretation of field lines originating in the jet versus the accretion flow?
Yeah, I'll talk a little bit about that in a second. At this point, it doesn't say anything about where the energy is originating. It just says what direction is it traveling. And so I think to really sort of hone in on BZ, you have to track this energy flow over a variety of scales and go as close to the event horizon as you can. I'll talk about that in a second.
I just have another question.
Yeah.
So, because you see a jet, would the conclusion, if you see the opposite side peaks, be that the angular frequency is negative, or is there any other option?
Yeah, I think there could be several options if we had seen this image. One would be that, yeah, maybe our interpretation of the angular speed was wrong, and maybe the field lines are actually rotating in the opposite sense. A more likely explanation, I think, would be that we just don't understand the Faraday rotation, or we didn't understand where the emission is coming from. And so, you know, if there's a lot more Faraday rotation than we think, for example, it could twist, it could change the sign of the spiral. That's a very annoying systematic we have to deal with. But yeah. The point at this level is not so much that we know exactly what was going on, it's just more that everything lines up more than you might expect. And then in a couple slides, I'll look at more detailed models. Okay, so yeah, like I said, ignoring Faraday effects and everything, this simple cartoon model implies that we're seeing energy outflow. And so the question immediately becomes, can we test this with more complicated models? Does this sort of connection between the direction of energy flow and the sign of this quantity beta 2 persist as we increase the complexity of our models? So the first thing we did in this paper was to turn to semi-analytic models. So here we're sort of fixing the magnetic field structure to a BZ monopole. So we know that energy is outflowing in this BZ monopole. We fix the direction of the angular, we fix these overall coordinate axis to be into the page, and we look at a variety of different velocities. So in this case, we're allowing sort of the plasma velocity to take many different values. It could be Keplerian, it could be retrograde or prograde, it could do many things in between. And we look at sort of the effect of the plasma velocity on the overall polarization pattern we observe.
This is optically thin.
Yes, this is an optically thin case where we have only midplane emission. Yeah. So here, yes, the fields are fixed, the midplane emission is fixed. Really, the only thing we're exploring is like, does the plasma velocity have a significant role? Because the relativistic aberration of from the relativistic moving plasma could change this beta 2. And in fact, we do see that it shifts around the beta 2, but never so much, except in the very low spin case, to change the overall sign. And so this overall sign of angle of beta 2 remains negative. It remains what we would have predicted from the cartoon picture, even under this huge range of different velocity models, which can, yeah, so like I said, span from prograde to retrograde.
So the changes in the low spin case is just because of relativistic effects?
Yeah, I think it's because in this case, we have pi, right, this is basically a toroidal polarization pattern. And so small changes in sort of these individual polarization vectors from aberration from the velocity model can sort of shift you over that line. But by the time you're wound up enough to have fields that you get from these higher spin cases, these small shifts encapsulated by the width of these distributions don't push you over the line. The other thing you immediately see from here is that there's sort of a systematic dependence on spin. I'll get to that in a second. Okay, so that's analytic models where we kept a lot of things fixed. The next thing to do is look at simulations, which don't have many fewer things fixed. And in
Does
particular,
that last chart mean that the high spin gives you weak outflow? Because you're closer to arg beta to 0?
so arc beta 2 0 corresponds to being in this more radial state, right? Which corresponds to the phi component of the field being larger. And you tend to have, in fact, a stronger outflow. But I think that's more about the angular speed is also increasing. Because this angular speed is sort of half the horizon angular speed in BZ models, right? And so that is increasing as you go. Okay, so in simulations, we now have turbulent magnetic fields. We now have all the Faraday effects and propagation effects that we included. We have a variety of temperature models. The emission could be coming from many different places. And in this particular set of simulations, I should step back and say these are all MAD simulations. So in sane simulations, the story is quite different, but assuming we've settled on MAD simulation for M87 from their previous analysis, we can just look at them. In a set of simulations that Ramesh ran a couple of years ago, we can just look at this angle of beta 2 in these individual turbulent images spanning a large range of different emission parameters and then see what they give us. And we can see that from these two panels, here on the left are the prograde simulations where we start the disk co-rotating with the black hole at large distances. On the right are the retrograde simulations where the disk is counter-rotating with the black hole at large distances. You can see that, again, with a small exception for most of these retrograde simulations, you always see arc beta 2 to the left of this line, which corresponds to this picture of energy outflow in our simple model. And this sort of fact have been known for a long time, I think, well, since 2020, since Daniel's first paper introducing the R beta 2, but I think that this is the first time we've sort of understood that from this sort of simple conceptual picture, that this is the sign that you automatically need if you're fixing the angular velocity of the black hole to be into the page as it is for M87. This is the sign it has to be if you're seeing magnetic field lines that are carrying energy out.
So Andrew,
Yeah.
so as you said, you are assuming that the black hole spin is pointed into the board, right?
Yes.
Fine, that you're holding fixed.
Yes.
And the result here is it doesn't matter whether your disk is prograde or retrograde,
Yes.
you'll always get these negative beta 2s.
Yes.
Good. And that's because, the black hole is spinning in a particular sense.
Yes.
But the retrograde guys are actually changing the direction of their orbital velocity. And this is what Angelo focused on
Yeah.
in his paper. So one would think that any disk emission from the retrograde guys will actually flip sign when you go into the outer regions,
Yeah.
right?
No, absolutely. I think that's what this sort of
So that's coming from
partially what
larger
this is
radii, I
happening.
think.
I think this is my next slide. So I think largely what's happening is at 2-3 gigahertz, we are seeing things that are co-rotating with the black hole, right?
They have forgotten the disk.
They have
Forgotten the
not,
disk angle
not
velocity.
entirely, right? Because there is still these distributions are shifted relative to each other. So there is an overall velocity shift.
Yeah.
But they've forgotten enough in the sense that they are co-rotating, and so they don't have enough. The field is going in the opposite direction of the black hole spin, as it has to be in the case where it's coming from sort of outflowing thing, line with the black hole spin, right? But yeah, there is still a systematic shift.
So, Andrew, one point about that plot. You go back one. Minus 180 is the same as 180. Mhm.
Yes, this is a difficulty in these interpretations.
It just converges.
Yes.
Like the left part of those curves, those are just a continuation of
Yeah.
those curves.
Yes, that's correct. Yeah. So I think I think some of this is, yeah, you can't think about it as maybe that we should have like a circular way of plotting this around like a ring or something. Yes, that's definitely correct. I think when you're right on the boundary, it becomes a little harder.
And what is the energy flow in or out at 180?
Well, at precisely 180 in the cartoon picture, it would be 0 if you would have no radial flux field component. But I think you can get very close to it, right? But yeah, this is also of course, because you can see also it corresponds to the lower spin cases, which also have low to 0 energy outflows. Okay, this is just sort of some plots from the simulations to say exactly what I was saying in response to Ramesh's question. So here you have a retrograde simulation on the left of these panels and a prograde simulation on the right. And you can see that if we look at just the field line angular speed, it's much higher, first of all, in the jet region where the fields are being wound up by the black hole. But the sign, importantly, on the prograde simulation is consistent all the way in the disk and jet, where you have co-rotating fields everywhere. But in the retrograde simulation, you have a negative angular velocity in the disk, where the initial conditions are telling you that the Keplerian disk or the disk is rotating counter to the black hole spin. But by the time you get to the close enough to the black hole where we think most of the EHT emission is coming from, everything is co-rotating. And similarly, in the magnetic field sign, the sort of this ratio flips between the negative and positive spin case. Yeah, and this sort of overall, this sort of effect of the black hole and having everything co-rotate by the time we were in the EHT emission region was, I think, first pointed out by George in 2021, but also looked at in Angelo. Okay, so in the last part of this section, I will briefly talk about spin dependence. So we immediately saw that these distributions here have a key dependence on black hole spin, right? As you go from low spin to high spin, you become more radial in your polarization pattern. Your beta 2 distributions march from left to center in this plot.
What is the blue line here, actually? In
The blue line here is the M87.
No, not here. In the next slide.
Next.
Yeah.
This is the sigma equals 1 surface, which is sort of hard to define in these averages actually, but this is roughly where you transition from plasma dominated to magnetic dominated waves.
And you eliminate that in the images you showed.
Yes, I think so, yeah.
That is sigma greater than 1 was disregarded.
Yes, I believe so, yeah.
Okay.
But that's, if I get to it, I'll have a brief comment out of that. Yeah.
So,
I really like to know.
Yeah.
So does this mean the retrograde spin case is the innermost plasma isn't taken into account in the image?
Yeah, I think it's hard to directly, so yeah, if you were to say, like, we cut out this
Yeah.
section because it's inside sigma equals 1, it's important to remember this is an average and the images are all generated from snapshots, which, you know, could have different sigma distributions in this. Averaging these quantities in GRMHD is always confusing to me. But yeah, certainly if you were to just make an image of this flow, you would not have any emission here. Whereas in the prograde case, you would have this sort of central region. But yeah, I think in the actual 3D simulation. But yes, it is, if in case I don't get to it, I will say, in MAD simulations, you have sigma equals 1, sigma greater than 1 regions very close to the black hole where emission may be very important. So I think it is a bad choice to always disregard sigma less than 1 emission, greater than 1 emission in MAD simulations. I'll talk about that more hopefully. Okay, so the effect of black hole spin. We can see that it changes the beta 2 sign. This is just coming from the fact that in the BZ mechanism, the field is wound up by the black hole spin, and it's wound up more as the spin increases. So you can see this in these nice pictures of the BZ monopole that George generated, where in a low spin case, you see that the fields are wound up, but in sort of a slow sense. But in the high spin case, the fields are wound up so quickly that by these scales out here, they look like they're basically purely toroidal. But the key fact is that they're always winding them up so that this overall sign is preserved, basically so that the field is dragged behind the black hole. Is again fixing the direction of the angular momentum. So this angle increases with spin. I think this sort of overall effect has been known for a while, but the nice thing is that this immediately maps into beta 2. And we can see that both in the GRMHD models here in these distributions. This is a different set of GRMHD MAD models than the one I showed previously, but it shows the same trend. And we can just map an analytic model right on top of that. It has the same trend. And so increasing this field winding both increases the pointing flux and makes the observed polarization pattern more radial. I think this, you know, if we calibrate all of our uncertainties correctly, and I don't think we're in a state to do that quite yet, we can use this to measure spin in MAD7. Okay. And the last slides in this section, I want to talk about how we might use this to test BZ. So everything I've said sort of gives me confidence, at least, that we are seeing energy outflow on the scales of the EHT, but doesn't necessarily answer the question about where that energy is coming from. If you believe the simulations, the energy is almost certainly coming from the black hole, because BZ is the dominant source of energy in the simulations. But you know, we can still play devil's advocate and say that maybe our simulations aren't capturing everything. There's still some alternative model that we're not taking seriously enough. And so my two proposals for sort of answering those questions and sort of unambiguously telling answering where this energy is flowing from are basically both related to looking at beta 2 or the polarization over a variety of scales. So if we look at, right now we're basically looking at one ring, we're looking at one average image with one beta 2, but what we see in the simulations is this beta 2 changes actually quite a lot over a variety of scales, which we might be able to probe with the future EHT. And so here I'm zooming in to the horizon, going closer and closer to this lensed image of the horizon called the inner shadow. And you can see that if we just look at the beta 2 plot, again, this is another plot that was inspired by Angela's work, you see that this beta 2 increases quite a bit as you go from sort of the EHT scales, which are roughly the same as these photon ring scales, out to the horizon. And this is just coming from the fact that the angle of beta 2 is that the fields are being wound up. So the fields are more. No, it's not just that, actually, sorry. There's also increasing effects of GR, so it's hard to interpret. But there is a precise prediction that you can make from these BZ models for exactly how this field windup is happening. And if you could observe that trend, you should be able to compare it directly to data. The second thing, which is the project I'm working on right now with Zach, who used to be here, is trying to zoom out and look at these fields, these evolving polarization directions in sort of the extended jet, not just in the region close to the black hole. And so this is again motivated by the fact that hopefully with the next generation EHT or upgrades to the EHT, we'll have enough sites and larger bandwidth to make these nice images of not just the emission close to the horizon, but out through the extended jet and illuminate the connection between the two. And what Zach is finding in sort of preliminary results is that the jet story is a lot more complicated because you have more velocity pointing along the line of sight, and that relativistic aberration becomes important. But I think not so important that it completely eliminates this connection between the beta 2 that you'd see at a variety of scales and the spin. And so definitely keep an eye out for his work. Hopefully we'll have it done in the next few months. Okay, so that is the end of that section. I think we have 5 more minutes. Any questions? Okay, I'll then just speed through the last section, which is on how we can better simulate the black hole jet connection. This is a paper which I'm almost done with. I'll hopefully be submitting this week. It's sort of a left turn from the previous discussions, but I think it's related by the fact that, we want to simulate these jets and these near horizon accretion flows as accurately as possible, to sort of include all of these difficult physical effects which we have to account for, and using relations like the one I talked about on the past slide to measure black hole spin and probe the BC mechanism. We need the best simulations that we can have, and our current simulations have a lot of issues, and this is talking about a proposed method for addressing one of those issues. Okay, so the main issue I want to talk about is that the simulations have a hard time dealing with a fluid that is very highly magnetized. This is just because the GRMHD codes conserve the total stress energy tensor composed of matter and electromagnetism, but sort of disentangling the two can be difficult. So in this limit sigma greater than 1, where sigma is the ratio of the magnetic field squared to the density, the numerical codes can really struggle to recover the fluid quantities from this total stress energy, and they can crash. And so the way that this is dealt with in GRMHD codes is to just sort of artificially cap the sigma, so prevent the magnetic field from going much greater than the plasma density by introducing this sigma max, which is usually around maybe 100 or a few hundred. And this keeps the code stable. It allows you to still have a magnetically dominated jet because you're still getting up to sigma hundreds, but it doesn't allow the jet to become as magnetically dominant as it might be in reality, where we might expect the sigma to climb to even higher values if this funnel becomes completely evacuated and it's completely described by magnetic fields. And sort of a key signature you can look of in these sort of snapshots of, this is the plasma density in a slice of a GRMHD simulation. A key signature you can look at for the effects of these density floors, or this limitation on sigma, is this sort of halo around the black hole. That's always produced just by this flooring material. We'll always see that in slices through GRMHD, at least the mad GRMHD simulations. Okay. In addition to sort of being aesthetically unpleasing, the sigma ceiling is annoying when it comes to producing images. So this is some images from the 29P paper I mentioned, but basically where we looked at the effects of changing sigma cut in a particular simulation, and you can see that if we include different material at different sigma in our radio transfer, you get different images. And so for a long time, the choice has been to always cut sigma, so entirely disregard material that has a sigma higher than 1 in the simulation, and we're producing images. This is sort of motivated by the fact that we have all this artificial material at these higher sigmas. And you can see that once if we completely remove the cut and we include all of the material in the simulation, which includes all this artificial floor stuff, you get an image which is sort of dominated by this floor material. But there's a lot of different choices in between, and they can all sort of produce different images. And so we use these sigma cuts in producing these images from simulations because we don't trust our high sigma, our high magnetic field material, but there's a lot of reasons to be wary of them, I think. They can have a large impact on our analysis.
How do you propose 1 case? So like 10.
That's a good question. I think it's sort of just the lore that 1 is sort of a safe value because you're nowhere near the ceiling, and you're also below the point where any uncertainty in the sort of trade-off between magnetic and fluid energy density can affect your fluid temperature. But we argued in this paper, I think, that we wanted that 25 is a better choice. But yeah, I think it's still a little bit. Okay, so I only have like 1 minute left, but the point of this section is that in this new paper, which hopefully we'll post soon, we are proposing to have a new approach for dealing with this problem. So instead of these density floors, we couple GRMHD to force free electrodynamics in this jet region. So when you have very high sigma, you can approximate the dynamics of GRMHD by the force-free equations, where basically you disregard the matter part and you just have the electromagnetic field operating under these force-free equations. This doesn't, of course, tell you everything about your system because you still probably have a plasma in there somewhere. And so you need to introduce additional equations to solve for things like the field parallel velocity, which the force-free equations don't tell you anything about, the fluid density and the fluid energy density. I can answer questions about how exactly we treat those in this particular scheme that I'm proposing. Basically, the idea of this method is to modify geometry code to transition to force-free evolution in this high sigma region. So to sort of switch from standard geometry to solving for the magnetic field under the assumption of no back reaction from the plasma, remove the requirement for density floors, and hopefully do this all without major code modifications. You basically do this by solving two different sets of equations and sort of stitching them together depending on the local sigma. Basically, we solve a force-free set of equations and a geometry set of equations based on the same underlying primitives as we go from one time step to another. And we, like I said, transition between the two. I can get into more details if people have questions.
Yeah.
Yes.
Shouldn't it be possible to see energy extraction just from the force-free equations without,
Yes.
is that what's the status of that without?
Yeah, so everything I said about the sort of the analytics in this previous section all applies, equally well in force-free and MHD. This is the Poynting flux equation in both force-free and MHD.
But also I think simulation, pure force-free has been done in the past. McKinney did it, and I think Tchaikovsky did it.
Yeah.
And of course, they produce BZ, works beautifully.
And with the energy coming out and the
Coming out of the black hole, it causes Poynting flux.
Yeah.
Andrew is saying, do both. That I think has not been done by anyone.
I thought for the VSID model, the power could not be as high as what the predictions are, and that's why perhaps having a hybrid model would help.
Yeah, I think the reason I'm mostly interested in doing the hybrid case is because we know at least that the GRMHD do a pretty good job of producing the images. I haven't seen any images from a pure force-free simulation. That would be interesting. Of course, you have to have some way of painting on the plasma on top of the force-free, which is questionable. This approach that we're proposing, I think, is nice because you have GRMHD inflow out here. Everything is low magnetization as described by GRMHD. The fluid and magnetic field pile on the black hole. It launches this jet, and you create a force-free region, but you can still advect the density through that force-free region and just sort of say it's decoupled. The density is just doing what the magnetic field tells it to do. And so you can still have some density in the jet. You still have some emitting plasma in there, but it's sort of just being sourced consistently by the disk. Okay.
Have people tried to solve the force-free analytically? Is that out of reach?
I mean, there's like the BZ, right? But give me like in 3D.
Evolution one.
No, what?
The time evolution.
Would it necessarily be time dependent? I mean, it could just be a stationary.
But Cranford and Snag did that.
First month.
Yeah, first small spin.
Perturbatively in the spin. Yeah.
Yeah, but it was analytic and
Yeah.
But and didn't need it do that for the ultra high spin kit?
I mean, there are analytic solutions known, but none of them exhibit energy extraction as far as I know.
really,
They're just not the right. They're not really, they don't correspond to the physical setup as far as I know.
Yeah, I think actually in the appendix to the previous paper I was talking about, Alex went through all the existing total fully analytic solutions to force-free. And yeah, I think as you said, that none of them that aren't perturbative show energy extraction. I think he has dreams of doing the full monopole in force-free, but I think you know more about this and it's very hard. Okay, so last minute, I'll just say that we have now compared this model, this sort of approach to doing hybrid force-free GRMHD and standard GRMHD in a set of two simulations, relatively low resolution, but both 3D. MAD simulations with the same spin and with everything held fixed except for switched this two approaches for dealing with high magnetization regions. On the left here, we have the plot of density for MHD and the plot of sigma. And you can see that in the jet region, sigma is capped and the density is also relatively high, and you see this characteristic halo thing. When you have the hybrid approach, instead, in the average, you can get to very low densities. You can evolve to very low densities in the jet, and you can climb to very high sigmas, up to 10 to the 6. You can see this even more when you have these sort of slices at different radii, and you're looking at the polar profiles. In standard geometry, these are capped, and this is all floor material. Whereas in the hybrid case, we're just allowing it to fall naturally to the value it wants to in this evacuated region. Of course, we're not necessarily doing everything correctly in the jet, right? There might be other, it's still an approximate solution in that region, but I think it's potentially a better approximation than the flooring approximation. Okay, so lastly, this has an effect on images. In standard GeoMHD, if we sort of increase the sigma cut to infinity, you get this sort of stuff in front of the image. For all the floor material in the jet that you're looking down through. Actually, in these simulations, it wasn't as big of an effect as I thought it would be. They were actually better behaved than I thought, but anyway, it's still there. Whereas in hybrid simulations, if you have a sigma cut 25 and you have sigma cut infinity, they look the same. So there's no ambiguity there. You can just increase the sigma cut to infinity, and you'll get the same image at the end of the day. This is also apparent in the light curves. This is where I wanted to stress the point that in the hybrid simulations and the MHD simulations, we see a substantial difference in the light curves between the sigma 1 cut and the sigma 25 cut. So that's the difference between this dotted line and the solid line here. But in the hybrid simulation, we see no difference essentially between the sigma 25 and the sigma infinity cut. So in the GeoMHD simulation, there's still a difference there, and that's coming from the floor material. I take this to mean that sigma 125 emission is important. It contributes a lot, even in this sort of slightly better approach where we do the hybrid GeoMHD. There's a lot of emission coming from there, at least in this particular model. We have questions about how much it can be affected by things like particular choice of inversion scheme and GeoMHD, and I think there's some systematic uncertainties about how reliable that emission is, but even in the hybrid approach, but I would claim that it's likely to be important. This is mostly coming from the jet sheet, but you transition from low to high magnetization. And so I would argue that we should be looking at the sigma cut in more thoroughness in future GHQ. Okay, so that's the end. Thank you for staying a few minutes longer. And yeah, here are my takeaways. Happy to take any questions.
Thank you, Andrew. We have additional questions. Please.
High sigma means a larger field or smaller plasma?
Oh, good question. I think in the, if we're looking at the differences between these two simulations, it largely means a smaller plasma.
Okay.
Because that's what, the MHD is lowering sigma by pumping artificial plasma into the jet. The jet power in the two, for example, is pretty
So basically going to high sigma doesn't mean extensive cooling, right? Because it's the field is roughly the same if it's lower plasma. Or is it both, actually?
I would think we'd have some misunderstanding. I think you'd have more cooling in the MHD case because the density is higher. But in the case where you have all this floor material, it could be
That's
artificial.
going to be my question, temperature.
Yeah.
Because the emission is going to be determined by temperature
Yes.
and the density, of
Yes.
course. What is the temperature?
This is the
Okay, I
continuation.
Yeah, exactly, Nisha's question.
I did not put this in my backup slides, but I do have it in the draft. Come on. Okay.
You can see this guy.
Basically, what we see is that the temperature looks quite similar on the jet sheath, but in our approach with hybrid, it is cooler in the core of the jet. But that might just be because of the assumptions we make for evolving the plasma in the jet.
Yeah. So less density and less temperature in the core of the jet.
in the core of the jet, yes.
So really it doesn't radiate.
Actually, in this case, I guess it's sort of slightly higher on the sheath. But yeah, in the core of the jet, it's slightly less.
And that purple line is sigma equal to one.
That's sigma 1, yeah.
Any final question?
Does it affect the light curve variability?
Oh, that's another good question. I have not looked at the variability yet. I would say just by eye, the light curves look similarly variable, but statistically, I have.
Yeah, I think we can continue over lunch and let's thank Andrew again.
This is really good. Stitching the two together.